Okay, so welcome to in-person Cognero Lab. So in this session, we're going to be starting off with some stuff having to do with Nissl stain. Now, I know we talked a decent amount about it in class at this point, but we do have a few refreshers that I want to go over. And so I just want to put out some reminders. We have the origin of the Nissl stain being used as something that can highlight RNA, and neurons are chock full of RNA based on them having all sorts of different proteins and functions. So they need a whole bunch of lines of code to make those proteins to have all those different functions. The staining chemical, it's not too important what exactly it is because multiple chemicals can actually serve the same purpose. So we use this stuff called cresol violet, but there are other things with different names that basically do the same sort of RNA staining. So this is not a property that's specific to just this one chemical. And what it'll do is it will differentiate between gray and white matter. So by that, I mean, it will show us distinction. It'll help us be able to visualize them separately. Gray matter will be a darker purple color. White matter might be stained lightly purple, but definitely there will be a lack of staining by comparison. Even between different parts of gray matter, there might be different amounts of staining because different parts of the brain have different densities of neurons. Some are really packed tight, other ones are a lot more sparse. And so we'll see some examples of that in some of the pictures that we will look at. Now, it begs the question, we're going to go through this process of putting brain sections from rats onto slides, staining them, and then looking at these and trying to match them with the rat brain atlas. Why go through all the trouble to do this? Well, something to consider is that although we know that rats are not people and vice versa, despite our own internal feelings about some particular people, it is one of these things where they are a good model for what happens in the deeper parts of the brain, specifically the subcortical areas. Remember, cortex is wrinkly outer shell for us, smooth outer shell for their brains. And so there's a lot of distinctions with those brain areas, even though they're generally laid out similarly. The subcortex, all the other areas beneath and within, those are laid out and shaped in a lot of similar ways. In fact, if we can find the connections going to certain brain regions in the rat, we can be nearly assured that those same connections will exist in the human brain. Now, things will certainly be scaled up because we know that even if the brain regions are very similar, the rat's nucleus accumbens, for instance, is going to be very tiny compared to the one that's in our brain. But it's more of a scaling up thing rather than any sort of fundamental change in what the connections are or where these brain regions are in relation to each other. So for us, our nucleus accumbens is in the same general place in the brain as where it might be in a rat when we look at all the neighboring brain regions. And so this is one of those things that we could generalize from learning about in rats first. And this will also be a good preface for when we look at sheep brains, which more closely model what a human brain looks like in about 2 weeks from now. So that's kind of why I think delving into this first is good. Plus, it gets us used to looking at the brain in at least some dimensions. We look at 2D planes across a 3D or another axis of extent. And so we'll get used to flipping through pages of the brain, so to speak, and get used to where things are in those coronal sections. And these, I think, will help prepare you a little bit more for the sheep brain lab when we're actually taking the brains and cutting them up manually by hand. So I have a few general goals here. One is that you'll become a lot more acquainted with the stereotaxic atlas of the rat's brain. I say rodent brain here because at some points I was using the mouse brain atlas, rat brain atlas. As far as the way the brains look, they're very similar, just again, sizing differences. When we apply the Nissl stain and also look at pictures within the atlas, you'll get a little bit more used to defining certain landmarks, as I usually call them, certain things that really stand out in the stain as, oh, that is this particular region. And I know it because there's all these other things around it, and it has this shape and this pattern. And so these are things that we can use as tells for us. Then, after we do our own staining with our own slides, we will try to take pictures of those slides and match them with Atlas pages in order to find 6 regions of interest. And so I've given the 6 lists, the 6 regions of interest in this document here that you're going to try to find. So you're going to get used to finding them first in the Atlas, and then we're going to see where we can find them in the actual sections and tissue. Take pictures of those, and then for the assignment, draw boxes around the areas of the pictures where they exist within. The boxes don't need to be hyper exact. I do have a margin of error built into like how these things are graded and corrected, so people don't have to worry about it unless they're like looking at the totally wrong end of the brain or something. So I think that people are going to be a little bit good at knowing generally where to find these things. And depicting the findings as a results section in style of such a section from an academic journal article. This isn't going to be something that's going to be painstakingly, carefully crafted. This is just getting you into the mindset of, oh, how do I want to make this figure look, and how do I make it look at least decent, if not good? So again, not going to be super demanding about that aspect of it, but I still want to kind of take what you see in those pictures and maybe put drawings around the area of interest, figure out how you want to label it in a clean way. And this is definitely something that having experience with the image editing lab in the previous weeks will have primed you for, so you can kind of jump right into it when you're ready. All right. So now that we're going to actually take a look at the Brain Atlas, we'll follow along with what I have on screen, but if at any point you want to dive in on your own laptop, I suggest doing so. If you have not downloaded the PDF file for this, you may want to do so even now, like while we're waiting. You can feel free to kind of just wedge yourself into wherever space you have to do that. If you don't have a computer with you, that's fine. You could always use any of the computers here on the wall side. And again, you don't have to download it, especially if you're going to be partnering or trioing up with people, which is allowed for this lab. All right, so while you're downloading that from the Moodle site, the reason why I say to download is because this file is about 400 megs. So it's a beefy PDF, and we'll see a little bit why in a bit. And the reason why I have you download it rather than just opening it up in your browser is that usually if you open it up through a browser, you don't have the full functionality of the buttons in the PDF thing. And so those are actually illustrated right here on the first page, where when you actually click on any of these lists of contents, it'll direct you straight to the page of interest. That's not all it does. There are a bunch of other things we'll see in a bit, but if you try to open it up in something other than Adobe Acrobat Reader, it may give you like some sort of yellow warning box. And so that's why you'll want to try to download it as a file to your computer and then open it with the Adobe Acrobat. And if you do have problems with that, we can kind of go over that later. But for now, you'll just kind of watch along as we go through this. So Paxinos and Watson, the authors, had painstakingly taken a rat brain, or well, a few different rat brains, and sectioned them down section by section by section. And they did this coronally, and then sagittally, and then horizontally for 3 different brains. And they use these brains as archetypes for the typical rats of this strain and species. It may not identically match every single rat that exists on the face of the earth, but it will give us an approximation to make certain assumptions from. And in addition to having different views of the brain in separate sections here, they also give us an extensive list of what the structures are that they've mapped and the abbreviations they use in those maps. Because they're not going to give you the full name right there on the pages. One of the features of downloading it in Adobe Acrobat is that when you hover over certain things, it'll actually list more information in a pop-up box. And so that's one of the reasons why I'm like, downloading this is going to get you a lot more out of it rather than having to flip back and forth through the whole thing. And we'll see some of these things in a bit. Lastly, one of the most important parts is that we have a section called plates, where for every figure where we have a map of a brain section, there is a corresponding stain section that they align that with. And so we'll see some of that in a bit. Okay, so let's take a look. We're gonna just jump to page 14. And I'm going to just blow this up, but in a second. First, this lower part of the figure illustrates the rat skull looked at from the side. When we are trying to do rat brain surgery, or human brain surgery for that matter, we need to know where we're putting stuff into the brain. We can't just decide we're going to aim for this general spot and know we're going to hit the right region. We have to have something that tells us that information. This brain atlas can tell us how to do that surgery in a rat brain within a 3-dimensional coordinate space, meaning that it can tell us how far forward, how far to the side, and how deep we insert some sort of electrical recording probe, or if we try to destroy a certain brain region for either treatment purposes or for experimental purposes, where to target those types of invasive things. And without that information, we are flying blind. So we again get back to the rat skull, and in this case, when we are trying to do surgery, whether it's on human or rat, we have some way to affix the skull so it's not wobbling around during surgery. For humans, there's this sort of like cube type cage that does it around the head. For rats, while they're anesthetized, they end up having their snout rested on top of an incisor bar. And then additionally, there will be these sort of things called ear bars that go into the sockets of the ear without puncturing the eardrums. And these hold the head in place in a flat position. When we expose the skull surgically, we don't have to take off all the skin, thankfully. We just take off enough to see what we need to see and also over the target of our interest. When we look at the skull, the top of the skull shown in the upper part of this figure, oh, that's not what I wanted to do. When we look at the top part of this figure, we see these weird squiggly things crossing over. The human skull, too, has these squiggly things. When we are developing in utero, and even after we're born, these are still kind of half in development, the plates of our skull are still trying to fit together and are still kind of malleable up until a certain point. Once they actually fuse together as just separate pieces of bone, they create what are called fixed joints. It's kind of weird because we think about joints being flexible things, but this is one example in which bone connects to bone, but it's still not supposed to move. It doesn't move. So there is this sort of separation of the plates right here. And we can use that in order to find our reference point for surgery. So what I mean by this is that if we don't know where to start in surgery to target what we're going to find in the brain, then again, we're flying blind. We have to have some place that is zero, our starting point. That a lot of researchers use is bregma. And so this bregma reference point is where the fissures of the fixed joints of the skull do this sort of crossover point, where it's either like an opened up Y shape, or sometimes you can see the fissure going forward from there. It might be more like a psi symbol, trident type thing. And we use this again as our 0 point because the brain in the skull underneath is going to be generally in the same location across various rats. It's not going to be really far forward or back from this 0 point. So we can rely on the skull's shape and this 0 point in order to figure out, okay, from bregma, how far forward, to the side, and down do I move my probe to target this particular brain area? So we have things zeroed out at bregma, and then we figure out how much we want to change the coordinates in order to target the brain region that we want to do something to. Any questions or comments so far? Okay.
I have an unrelated question.
Sure.
About the joints. Is that why babies have like their little soft spot when they're born?
Yes, I believe that's related. Yeah. So, I mean, the thing is that babies' bones are also not like super durable. They are a little bit more malleable, which makes them perhaps less likely to be injured in some ways, but more likely to be injured in others. So it is a little bit of a tricky balance, but during that age when things are still developing, there is that malleability even of like bone structures. Not to say that it's like rubber, but still more malleable than adult bone. So we have this Bregma reference point, and that's what most people will use. There is a little bit of other information I'm going to mention because we'll see it on other pages in the atlas. This interoral line here, this weird dotted line. I mentioned that thing about how in the surgical device, they insert these bars into the ear to help hold the skull in place. Those are the ear bars, or the things that make this interoral line. Inter, between, oral, having to do with ears. So the line that is going between the ears. This too could be used as a reference location. And so some of the coordinates in this atlas do use that system of the ear bars and all that stuff. I don't, and so we're not going to bother doing it. But you will see interoral like on various pages, and I'll just be like, just ignore that. That's what that other thing is, just in preface. All right, so we have our reference point that things start with in this atlas. And I'll skip ahead to the next section in which we have our list of structures. So one of the ones that we'll be focusing on, for instance, is the nucleus accumbens. And the nucleus accumbens, it's tricky in the atlas because sometimes we'll have a name for a region and they just swap the words in the name around. So they call it accumbens nucleus instead of nucleus accumbens. What are you going to do? We're going to look specifically at nucleus accumbens core, and that is located down over here. And we see, let me just go to the left a little bit. We see that its abbreviation, if we're to see it in the atlas pages, is ACBC. Quick tip, when things are starting in lowercase, it usually means that it's a white matter type of region, or fiber tracts, or something like that, things that we might use as landmarks when we're trying to figure out what we're looking at. And things that start in uppercase, just the first letter, are brain regions or gray matter. The only exception to that being when we're talking about the fluid-filled pockets of the brain, the ventricles, of which there are few, and we don't have to worry about that too much. That'll come up more in the sheep brain lab. So we see accumbens core, and if we hover it over the abbreviation, it actually gives us a bunch of numbers. These are the figure page ranges. The atlas doesn't start counting page numbers until you start looking at the actual diagrams of the brain slices, or sections, as I call them. And so we can look at these page ranges, and this will tell us where to expect to see this brain region. So the nucleus accumbens core is on pages 11 through 29, and I know that these are the coronal view pages. 1666 through 171, those are the sagittal section pages. And then that leaves the horizontal section pages for the other numbers, 189 through 195. We're not going to worry about sagittal stuff. We're not going to worry about horizontal stuff. We're just going to stick with coronal. It's definitely easier to work with. And that's also because the sections we're using are coronal sections. So we're not going to try to do any sort of weird figuring out otherwise. Now, if we're to look for the middle of a brain region, as sometimes the assignment and the document suggest, we don't want to just go with the first number that we have. In other words, page 11 is the very, very front tip of the nucleus accumbens core. And so maybe we don't want to hit that. Instead, we want to go for where's the center of this region? And it can be approximation. There's another part where you're supposed to give coordinates, and I'll talk about how you do that in a bit. But when you're giving coordinates, there is a decent amount of leeway for like what qualifies as correct or close enough. So definite partial credit is involved with that whole process of figuring out the numbers and what fits best. But generally, you're going to try to go for the middle of the page range. So something like, I don't know, page 20 might be about the middle of the extent of the accumbens core from front to back, because coronal sections are kind of like flipping through the brain front to back as pages, as we'll see in a little bit. Okay, so now we have an idea of which page to flip to when we want to. So page 20, that's it. There is something else though, because I don't want to just give easy answers out right away. There is another thing that we're going to look at, and that would be the anterior commissure, which is up over here. We're going to look at the anterior part of the anterior commissure, ACA, which happens to be around the same general zone of the nucleus accumbens, maybe across a few extra pages. But we're going to try to target that because it's a much easier, like, specific target rather than a general area. And so the anterior commissure, anterior part is 8 to 33. So we're going to aim for, again, maybe page 20, just to make things easy. And after we go down into the next section, we can also see if you're trying to figure out what an abbreviation is that you're looking at, go to the index of abbreviations and it'll give you all that info. It'll give you the abbreviation first in alphabetical and numerical order. It'll give you the full name, and then it'll also give you the page numbers to find it out in all three views of the brain. To skip forward, one thing I know is that the figures, the actual diagrams of the brain sections, they start on PDF page 44. So if you're looking for a specific figure page, you add 44 to that to jump right to it. So if we're going for like page or figure 20, then adding 44 to that, we go for PDF page 64. So let's give that a try. Hopefully it'll give us the right location. 21, close enough. All right. So let me just zoom out of this to give you the whole view once again. So here we have a typical coronal diagram coming from one spot in the brain, relatively far forward. In this coronal diagram, we have a lot going on. We have X and Y axes. We have this thing saying interoral and a number down here. We have bregma and another number down here. We have all these little abbreviations that we'll zoom in on later. And so there's a lot to take in. Firstly, let's look at this bregma 1.56 millimeters. So what they're doing is, since this is supposed to be in 3 dimensions, but we're only looking at a 2D image, we have to know where this 2D image was taken out of, like index cards in a pile, which location it was taken out of in order. And so we know that this part of the brain, this slice of the brain, section of the brain, came from about 1.56 millimeters in front of that bregma point on the skull, our reference point. So when we're looking at that crossover of the fixed joints of the skull, if we were trying to find something that existed in this page, we would move our surgical instrument forward by 1.56 millimeters. There are things behind bregma, and those are just minus on the bregma thing. So if it's something behind bregma, if it's like 5 millimeters behind bregma, it would be bregma minus 5, whatever. All right, so that's an easy number it just gives us. The rest is for us to figure out. First, we'll look at the x-axis, and that actually starts at 0 in the middle, regardless of whether you look at the top or bottom point. And that seems a bit weird, but if we think about it, if we were to measure things from left to right, it might be a little bit harder to kind of do that compared to starting in the middle where the reference point is. The bregma does start right between the 2 hemispheres. And so we use the 0 point here to figure out how much off to the side in either direction we want to go. And so each of these numbers represents 1 millimeter. So 1 millimeter, 2 millimeter, so on. Each of the small dashes in between is 0.2 millimeters. We can use the grid as a little bit of a guide. And so I mentioned that brain region we're going to try to zero in on, this ACA. We're going to blow that up right here. See anterior commissure, anterior part. When I hover over it, it pulls up the pop-up box. Drag it down once again. We can use this lower axis to try to help us find where exactly it is. Approximately, where would you say is like the center point of the ACA as far as these numbers go? What number would you give? Yes.
1, 2.
I would say almost 2, maybe not quite though. Yeah, when you're at it from like an angle, it might be a bit tricky. So if not quite 2, what's another numeric guess? Because you're close with that. Yes.
1.8.
Yeah, 1.8. And once we get into like the hundredths place of decimals, then surgically it's like it it's too hard to actually hit something that time. So that would be really precise, and there are instruments that would try to aim for that, but there's so much variability that I'm not guaranteeing that we'll even hit it. To be truthful, if I were trying to target this, even having done rat brain surgeries over all the years, I would have plenty of misses that would be hitting around it, like here, 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 here. And then, some number of subjects would actually be direct hits. So it's not a guarantee even when you have this, because there is some variability with each rat. So the smaller regions are really hard to study when it comes to these things, especially in the rodent. All right, so we're gonna go with 1.8. So our medial lateral coordinate is 1.8. I say medial because that's the most middle part. Lateral is whatever's to the side of that. So we now have another number, and we know that if we're going to put something into the brain aimed at the ACA here, we're going to have to move 1.8 millimeters to the side of the bregma reference point. Which side? Whatever you'd like. Because if we're implanting it only into one hemisphere, then it's whatever hemisphere you choose. We don't expect this, you might have the question answered. We don't expect there to be hemisphere differences within rats like we expect with people, like left hemisphere for analytical piece by piece thinking, right hemisphere for holistic, whole concept metaphorical thinking. That stuff doesn't seem to be the case in rats. The most different hemisphere stuff that does occur, I think, is in like the more sex-oriented stuff in the hypothalamus. And that's like a very specific case. Most of the other stuff is going to be identical between the hemispheres. Was that your question or something else?
Something else. So if it doesn't matter necessarily which hemisphere of the brain, do you like say what you're using based on? So like we're moving it 1.8, it doesn't matter necessarily if that's positive or negative, like one hemisphere is not a positive.
That's correct.
Okay.
Yeah. Deciding which one's positive versus negative is a bit arbitrary. The trick is that if you're trying to put it in both hemispheres, you say plus and minus, or plus / minus. And that denotes that you're not just using one probe, you're using two probes in each side of the brain, located in the same target. Yes?
If you're trying to look at different things within a hemisphere, do you always stick to the same one? Like if I do the ACA on the right side and I want to do something else, would I also stay on the right side, or does it not matter?
Sometimes connections do go across the brain. So in some cases, one thing that comes to mind is some research I've done involves track tracing, where you inject a chemical into part of the brain and then you see either where it connects to or what connects to it. A lot of the time, the connections for a brain region exist within the same hemisphere. Sometimes they cross over, and that's where that might be relevant, but it happens a lot more rarely than what you'd expect. So for the ACA though, since that's a large fiber tract region, I think that's going to be like funneling a lot of stuff from the very front of the brain to like middle parts of the brain within one hemisphere rather than crossing over. We do have a familiar character actually in this same picture here. It says GCC up toward the top middle. That is part of the corpus callosum, the main fiber tract that connects the two hemispheres so that they can both share information with each other. Otherwise, the two hemispheres would operate mostly independently. Any other questions before I continue? All right, so now we got our medial versus lateral coordinate, and we could decide positive or negative. If for some reason as a researcher, we're like, we're only picking the left side, then we just have to say that in publication or something. And then we have dorsal ventral coordinates. Now, one tricky part about this is that we want to stick to the y-axis on the right side because that's relative to bregma, because you'll notice that the numbers are in different arrangement on the left side. They start up at 10 and go down to 1 and 0 on the left side, but then they start up at 0 and then go down to 9 or 10 on the right side. The right side is one associated with bregma, so basically we ignore the left sliver of this whole thing forevermore. And then we can use this as our dorsal versus ventral coordinate figure outer. So if we're looking at this and we're counting it down from the skull surface, and we see that there's a little gap because the brain is not right at the skull surface in this case. When we're counting it down, whereabouts would you say the ACA is in this axis, in the y-axis? Yes.
7.1.
Yeah, 7.1. Yeah, 7.1, 7.2. Depends if you're aiming for like the lettering even, if you even want to be that precise, but that's definitely close enough in my book. So yeah, we have our DV, dorsal versus ventral coordinate. Dorsal being up, ventral being down. And so the way that we write these coordinates, I have listed in the document here. So let me just scroll down a smidge. Here. So we had our AP coordinate before. That was just given to us in the bottom right corner of the page, Bregma 1.56. In that case, you do want to specify whether it's positive or negative, because that makes a huge difference. Because there are both options in either direction, and they're going to be very different brain areas. So it would be it'd be AP for anterior versus posterior. AP plus 1.56 millimeters. So that's our front versus back coordinate. ML, we decided was about 1.8. And so if you were just aiming for one side, you could just leave it at 1.8 without a plus or minus sign. If you want to do bilateral, meaning both sides, both hemispheres, then you do plus/minus to denote that. And then DV, if you're using Bregma as a reference point, it's kind of assumed that you're only going to go down and not just up above the brain. Kind of silly otherwise. So I usually put negative in there, but I think it's assumed because that's the only direction you're going from 0 to go down. And so we would lower it in by about 7 or 7.2 millimeters in our DV coordinate. And so if I'm asking you to write down, hey, what's the center point of these brain regions, this list I give you? You find maybe an ideal page that brain region exists in, like the largest part of it, or maybe the middle of its extent in the coronal sections. And then you find the coordinates for all three of these things. The page will give you the AP coordinate automatically. Then the ML and DV coordinates are the ones you have to figure out using the X and Y axes. Okay, so I think for this next part, my plan was for people to actually look up 2 of the areas of interest and try to find their coordinates, the center point coordinates for those areas of interest. So in the assignment, it'll ask you for like figuring out, hey, where is this located? What coordinates would you give? I would like people to do that now for 2 regions to help you get acquainted with the atlas. And also that way I'm here in case you have questions. Stop recording. Yes. That thought, because here's the part that I didn't mention before. The other important part that relates to the Nissl staining. You'll notice that there are a few little buttons on the bottom. Again, as long as you open an Acrobat Reader, these buttons will function normally. It says plate, full screen on and off, kind of an obvious one. And home will send you straight to the table of contents. Plate is an important one here. So take note of where the ACA is on this page. And then when I click plate, you should be able to actually see what I was pointing to. So this is a close-up of a Nissl stain, about the same thickness as what we're working with. Or well, actually the sections I have for you today are much thicker and that's easier. More about that in a little bit. And so we could see that some of these features do pop out. For instance, we see that the corpus callosum is up here, this sort of lighter colored band that connects the 2 hemispheres, like I said. It kind of has a fiber tract that goes around and it looks like a weird bat shape, if you will, that you should be able to see. And the anterior commissure, the ACA, is this little lighter colored dot here. And so this is how we use the Nissl stain in order to find where things are. We could also see that to the bottom left and bottom right, there are some parts of the rat brain's cortex that are especially dense and have absorbed a lot of stain there. And so those are just very compacted gray matter. We also have these weird fang shapes. These are actually cross sections of the fluid-filled pockets this far forward in the brain, lateral ventricles that we'll see in the sheep brain lab again. But if you happen to be flipping through the plate views, You'll be looking at your sections that are stained. You're going to try to find a matching plate view. And if you click the button again down the bottom that now says figure, it'll send you right to the corresponding diagram page for it. And then that way you can start doing some of the math on, okay, where exactly is this located, or what am I looking at to help you figure out exactly what that is. One other thing is that when you're flipping through plate pages, you may see some of them look like this. This is an entirely different stain that we're not working with. I would love to figure out how to get this in the lab without having toxic chemicals around. Because this is obviously far more pronounced. This is something that stains for an acetylcholine enzyme. So we don't need to know about that particularly, but there are other staining options that can give us more information on top of what the Nissl stain can give us. And so in case you're having trouble trying to figure out what you're looking at in Nissl stain, if it feels like you're looking at a magic eye picture, you could always kind of cheat a little bit and look at one of these cholinesterase stains instead. And that might help guide you on what to look for when you look at one of the Nissl pages. And it alternates between this brown one and the purple one every other page. All right, so I think that's all I wanted to mention. Any questions before you go back to hunting down brain region coordinates? Yes?
Just to clarify, the Bregma coordinate that they give us is negative when we report the coordinate.
The Bregma coordinate, so if the AP, if the anterior posterior location is behind Bregma, it's negative.
It's negative. Okay.
And if it's in front of Bregma, it's positive. It has to have positive or negative though to make it clear.
That makes sense.
Yeah.
And it's just reflected on what it's given.
Yeah, so if we're looking at these coronal pages, it'll just give us it and it'll tell us like, if it doesn't have a negative sign, then it's plus.
Awesome.
Yes.
That makes sense.
Anything else? All right. So we'll just pause this recording again and we'll pick that up once we have some sections to play with.
Right.
Do you want to do